So this week we're going to talk a little bit about sets. So essentially, you have a set is something that we are going to work with. We're going to play with different integers and such. Essentially, German mathematician G. Cantor, he's the one who introduced the concept of sets. So a set is basically a collection of definite and distinguishable objects, and set theory forms the basis of all of this. So if you look at it, a set is an unordered collection of different elements. A set can be written explicitly by listing its elements using a set bracket. And if the order of the elements is changed or any element of a set is repeated, it does not make any changes in the set itself. Now, set theory forms the basis of several other fields of study and can help with counting theory, relations, graph theory, and so on and so forth. So in this case scenario, for example, you have a set n which has the integers 2, 4, 6 and 10. It has 4 real numbers. You have set f which is watermelon, strawberry and banana, and then you have set m which is again different varieties. So you have your monkey, you have strawberry, and then you have a number. So different elements that can still, and they still form something called a set. You have different types of definitions here. So we're going to go over an empty set. So an empty set is basically a set with no elements. It's called empty set and it's denoted by that. So it can also be a null, it can also be, that's your symbol for it. Now your null set is also an empty set. Essentially same exact concept, it just has those brackets and there's nothing inside it, so it's empty. Then you have a finite set, which is again a finite definite number of elements. Infinite, which is again infinite, you don't really have an order and it can change as it is. And then you have cardinality. Cardinality of a finite set is denoted by that. So mod of A, this is basically the number of elements in A. This defines that it is basically a specific set. All right, if we look at different other definitions, so set A in this case scenario, you have 2, 3, whatever numbers that are listed. Now the order of these elements do not matter. It doesn't matter, we can switch it around, the set still remains the same. It's more or less like our class. So it's COT 3100. Let's say we have about 50 students in this class. Whether if we had been meeting in person, you could sit in the first row, you could sit in the second row, you could basically mix and match and move every week or every other day. It still wouldn't change. It's still the set called COT 3100 for this semester. Now A is the cardinality, mod of A is the cardinality of A, which is the number of elements in A. So cardinality is finite, therefore A is a finite set because there are 4 numbers here. Now this belongs to indicates that an element is in a set. That is basically your symbol for belongs to, and that does not belong to. So it defines whether something is a part of a set or not a part of a set. And now empty set or null set, those are basically what your empty sets or null sets look like. You have different set builder notations. So basically then a set is defined by specifying all the elements that are included in that set and also satisfy certain condition. So let's say set A is basically equal to x belongs to z, where x is an integer multiple of 3. B on the other hand is a set where x belongs to z and x is a perfect square. So these are specific conditions and it includes all the elements in that set. Now universal set, it's denoted by this U. Essentially it is a set that contains all the elements mentioned in a particular context. So again, if I say COT 3100, it basically includes all of you, it includes whatever work you do and so on and so forth. Venn diagrams. Venn diagrams are represented basically, I don't know if you've ever heard of that. Essentially there are 2 circles. You define what's representative of each set and then there is an intersection. The intersection is basically what defines what's going on or what's common between the 2. So in this case scenario, let's say A is a set that has 1, 2, 3. So 1 belongs to A, 2 belongs to A, 3 belongs to A. B is a set that has 2, 3 and 4. So 4 is the only one that doesn't belong to A and 1 doesn't belong to B. So those two remain in their own set, but this becomes like a conjunction or an intersection between the two sets. Now subset, it's basically you have a larger set and then you have a smaller set that kind of fits in between that. So if everything's a part of A, or every element that's a part of set A belongs to B, then A is a subset of B. And that's basically the symbol that's used for subsets. Now, A is a subset of B implies that the domain of X belongs to X, where belongs to A, X, where belongs to B. A proper subset is basically if A is a subset of B and there is an element of B that is not an element of A, that is A is not equal to B, then A is a proper subset of B, denoted as A subset of B, proper subset of B. So if you look at this specific example, A is a proper subset of B implies is true if and only if A is a subset of B and basically you have other conditions that need to be satisfied, or you can denote it as that where it's not going to be equal. So let's say, to simplify this, let's say A is a set that has 1 2 3 4 as the numbers in it. B has 2 and 4. So B is a subset of A. So 3 belongs to A but 3 doesn't belong to B. Therefore B is a subset of A, proper subset of A. Now A is 1 2 3 4, C is 2 4 5. Now 5 is the number that belongs to C but 5 doesn't belong to A. Therefore C is not a subset of A. Everything has to go in there. If it doesn't go in there, then you're going to see different issues and we're going to call them different things. So if A is 1 2 3 4, D is 1 2 3 4, basically they're both subsets of each other. They're essentially equal. Now a power set of A, where it's denoted as P of A, is a set of all subsets of A. So this denotes all the subsets. Size 0 is that, size 1 is that, size 2, and so on and so forth. Size 3 is basically your power of set A. Therefore power of set A is equal to whatever is in there. And now if you wanted to look at the cardinality of the power set of A is 2 raised to the power of n, or modality of P of A is equivalent to 2 raised to the power of n. Okay. Now set operations. The intersection of A and B. This is basically denoted with that. That's your icon. It's a upside down U and is read as A intersect B. This is basically a set of all the elements that are a part of both A and B. So if we drew out a Venn diagram, you'd actually, whatever is in between, that's going to be your intersection. Now a union of set is denoted by a uppercase. It's just upside down of what intersection is, and it's read as A union B. So this is represented by everything between both of them. So everything has to be a part of it. Now you have a difference between the two sets A and B. It's denoted with a negative sign or a hyphen, and it's the set of elements that are in A but not in B. So A minus B, or A difference between A and B, is represented by that. So you have two sets basically. Everything that's a part of this equation becomes what's active. The symmetric difference between two sets is denoted by basically that, and it's called the symmetric difference between two sets. It's the set of elements that are a member of exactly one of A and B but not both. So remove this part, the intersection part, everything else is what you're going to look at when it comes down to symmetric difference. And the components of set A, denoted as A with a dash on top, basically belongs, is a set of elements in the universal set that are not the elements of A. So basically A dash is U minus A. These are your set identity rules. Keep this handy. This is required. You're going to need this at some point or the other. Basically these are the idempotent laws, the associative laws, and so on and so forth. These are basically, if you look at this, so idempotent law, for example, A, if you go back and you look at all the icons, again, you may want to write these down just because it's going to make it easy. So you have your intersections, you have your unions, you have your difference between two sets, symmetric difference, and such. So again, A union of A is basically A. A intersection of A is also A. It's basically like saying, am I me? Yes, I am me. That's basically what's happening here. Associative law, if A union B union C, then A is the union of B union C. Same idea, it's equivalent to basically if A is equal to B, B is equal to C, then A is equal to C. That's the idea here. Same thing with intersection. Commutative laws, this applies to the union and intersection as well. If A of A union B is equal to B union A intersection B is equivalent to B intersection A. Now if you have distribution, basically look at the parentheses, that's where everything's going to happen. So intersection B intersection C is a union of A, then A union B intersects with A union of C. Same exact idea on the intersection side of things, you're going to change signs. So you have A intersection of B union C, then A intersection B is a union of A intersection C. Identity laws, again, if A is a union of null set, then you have A has an intersection with a universal set, then you have A, so on and so forth. Just keep these laws handy, they're going to be useful. Now Cartesian product is basically you have a specific set that's defined. It's an ordered pair of items. These cannot be mixed and matched. You actually have a specific possible ordered pair, and then you work off of that. So the Cartesian product of A and B, or the first entry in an ordered pair is X and the second one is Y, and the Cartesian product, it's again for two sets, say A and B, the Cartesian product of A and B is denoted with your cross sign. It is, or a multiplication sign or product sign. It is basically a set of all ordered pairs in which the first entry is in A, second entry is in B. So A Cartesian product of B, or A cross B, is equal to a set which is X of X and Y, where X belongs to A and Y belongs to B. Let's say we have two numbers, A is 1 and 2, B is ABC. So you create this table, A has 1, B has 2, ABC on the top with B. Now multiply each thing. So this becomes A1, or sorry, this becomes 1A, 1B, 1C, 2A, 2B, 2C. Switch it around. No matter how you do it, if you decide to switch it around where you do B cross A, then you have A1, A2, B1, B2, C1, C2. Make sure the order remains right. So depending on who goes first, you're going to fill it out accordingly. Now partition is basically when you have two different sets and they're said to be disjoint if their intersection gives you a null set. Now if you have different sets or a sequence of sets, say A1 going through A10, it is pairwise disjoint if every pair of distinct sets is disjoint, which means A1 intersects with A2, it's going to be null set, and it doesn't matter which value of I and j. So whether it's A1 or A2, or whether it's A2 and A5, it's A1 and A7, so on and so forth. Whatever is in that set, if it becomes a null set, then you basically end up with a pairwise disjoint set. A partition of a non-empty set A is basically a collection of non-empty subsets of A such that each element of A is exactly in one of the subsets. So basically a partition is if you have, let's say, A1 going through A10 and it is non-empty, if the condition is A1 is a subset of A, A1 is not 0 or not a null set, and then A1, A2 and are pairwise disjoint, and A is equal to A1 union A2 union A1, so on and so forth. Alright. So partition examples looks a little like this. So let's say we have a subset A called A1, 2, 3, 4, 5, 6. A1 is gonna be, it's a subset which is A1, 4, 5. A2 is a subset which is 2, 3, and A3 is 6. Now A1, A2 and A3 form a partition because they don't actually have they don't actually intersect on any specific element. If you look at this, b1, where b1 is x belongs to r and x is greater than 1, b2 is x belongs to r and 1 is less than or equal to x is less than or equal to 3, then that's how that's going to appear. And then b3 is x belongs to r and x is greater than 3. These become partitions of R because none of them actually coincide, none of them intersect at any given point. And that's basically everything I have in terms of sets. Thank you.